Welcome to today's class. Recall that we are working under the assumption that P is a hyperbolically convex, locally finite fundamental domain for our Fuchsian group gamma. Recall also that whenever we are given a locally finite fundamental domain, it is possible to find a generating set for gamma defined in terms of the locally finite fundamental domain, namely by considering all those elements of gamma that do not take the fundamental domain too far away. Um, Today, we are going to refine this set of generators and we're going to start establishing some side pairing properties of each element. So let's take the set of elements of gamma for which p bar intersects gamma of p bar is a side of p, a gamma side of p. So this gamma star is contained in the set that I just mentioned, and take the corresponding set of sides of the polygon. Of course, by the very definition, for each element of gamma star, we have a side. Right? So we have this function, this obvious function, which is obviously surjective, right? Because precisely where every element, every side is comes precisely comes from at least one element of gamma star, so it is obviously surjective. And it's injective because of the lemma that we proved that whenever we are given two different elements of gamma minus the identity element, with the property that this triple intersection is not empty, we necessarily have that this triple intersection has exactly one element. Right? So different elements of gamma star cannot give me the same side because this triple intersection has exactly one element. Right? And this we proved like with the help of this picture. Okay, so we have a bijection between gamma star and S. Now we notice this. So given this aside, given an element of S, right? We of course have P inverse of that element, P inverse that element, and it is an element of gamma star. Now this element, by definition, I mean this element gives me the side S, right? So I have this identity. And if I apply the inverse in gamma of this element to this identity, well, what I obtain is this identity, right? Which I'm going to call iota of S. But the point is that this is again a side of P, right? Because of course this becomes this when I apply this element. But the fact that it's equal to this, it tells me that it has more than one element, right? So this is indeed a side. So iota of S is a side. So what I have is a function from S to S that to each element that associates iota of it. Right? It is an involution. With this, I leave as an exercise. It's quite easy to show that it is an involution. Okay, and now let's show that the subgroup of gamma generated by gamma star is the whole gamma. So that this set generates gamma. So this is the refinement that I mentioned at the beginning of the class a few minutes ago. So what we know is that gamma naught generates gamma. where gamma naught is, as I said, the set of elements of gamma that do not take p bar too far away, right? Which formally is this, that gamma of p bar intersect p bar is not empty. So in order to show that gamma star generates gamma, it suffices to show that gamma naught is contained in the subgroup generated by gamma star, because we already know that gamma naught generates gamma. So let's take an element of gamma naught. We shall show that it belongs to the subgroup generated by gamma star. So it is in gamma naught, right? So we know that this intersection is not empty. So take an element in that intersection. Uh-huh. And then, well, then we know that there exists a hyperbolic disk containing this point W, with the property that only finitely many elements of gamma make p bar meet that hyperbolic disk, and also that every element every element here has the property that the corresponding copy of p bar contains W. Okay, and moreover, by shrinking such disk if necessary, we can make it disjoint from any side of any nu of p, not containing W, right? Um, I mean, so W is either in the relative interior of a side, or is a gamma vertex, right? And then here are some other sides, right? So we can shrink NW sufficiently so that only the gamma sides of the new piece, only those gamma sides are that contain W intersect the disk NW. Right? Gamma sides of translations of P, not only sides of P, but of translations of P. Okay, now we can number. I mean, because of this property. I mean, because all the elements of sigma W have the property that the corresponding copy of P bar contains W. Um, Now we can number the elements of sigma W in such a way that the intersections of the copies of P bar under the elements of sigma W with the hyperbolic disk NW look as in one of these pictures, right? Um, this would be in case sigma W has exactly two elements, and this would be in the case it has more than two elements. Uh, sigma W must have at least two elements because of the way we took gamma and W. Um, okay, now right, and this union of all these intersections has to give me this disk, right? Because here in sigma W we put all the elements of gamma with this property, right? So NW is really the union of all these intersections. Right now, and the numbering the way we number the elements of sigma W is so that the image of P under consecutive elements of sigma W are neighbors, right? Okay. Now notice this. this, the intersection of nu naught of P and nu 1 of P is a common side of P and a nu 1 P. And the intersection of nu 1 P with nu 2 P is a common side of nu 1 P and nu 2 P, etc. Right? So we have all these intersections are common sides, right, of the consecutive copies of P. Um, so uh, so this is a common side of nu j of nu j minus 1 of P and nu j of P. So when I apply nu j minus 1 inverse to this intersection and to this and that, what I obtain is that P bar intersects nu j minus 1 inverse nu j of P bar is a side of P. Right? And so this means that this element uh, um, how to say, so nu 1 of P, so you see um, nu 1 of P has the property that P bar intersects nu 1 of P bar is non-empty. So this one, and it's actually a side of P. So this one is in gamma star, and then because of this, uh, nu one inverse nu two is in gamma star because it's side of P bar, etc. Right? So what I obtain is that all these uh, compositions are in gamma star, and you see from the fact that nu one is in gamma star, I see that then nu two is in gamma star, nu three is in gamma star, etc. Nu t is in gamma star. So all of these are, sorry, not in gamma star, in the subgroup generated by gamma star. So all of these are in the subgroup generated by gamma star. And this, and so what I have shown is that the set sigma w is in the subgroup generated by gamma star. But you see, but gamma is an element um, uh, is an element of sigma w because I took an element with this property, and so it must have because of the way I took w, it must have this property. So gamma is actually an element of sigma w. So gamma is in the subgroup generated by gamma star, and this shows this containment, and the theorem follows. Um, okay, now let's start analyzing this kind of side pairing properties of the elements of gamma star. Um, so definition: a gamma cycle in P bar, or a cycle in P bar is the result of intersecting a gamma orbit with P bar. Uh, Such set is necessarily finite because of the local finiteness of P bar. Um, namely, take an element of such a gamma cycle, so it's in P bar, and then it's a compact set. That's a point. Right? So and only finitely many elements of gamma have the property that this point intersects images of P. Um, so it must be so the cycle must be finite. Uh-huh. Its length is the cardinality of that intersection of this gamma orbit with P bar. The order uh, is the order of the stabilizer of any of its elements. So you see, since if I have a gamma cycle, all its elements belong to the same order. So the stabilizers of its elements are all conjugate inside gamma. So they all have the same number of elements. Right? So this is well defined. Um, Um, Notice that uh, any such subgroup is either only the identity or a maximal elliptic subgroup of gamma, necessarily finite. Um, Now, if C is a gamma cycle, uh, and we take its element, then so you see, at each element of C, uh, the polygon P subtends certain angle, which we call theta Z. Uh, and of course, C may have several elements, right? So there may be several angles. And then the angle sum of C is the sum of all such angles for elements of C. Um, okay, and now the theorem, an important theorem, says that for in every gamma cycle, the product of the order with the sum angle is 2 pi. Um, so for the proof, we are going to use this configuration again. So so take an element of C, and for every other element of C, uh, take an element of gamma that moves it to W. Um, so I mean, by definition of C, since C is the intersection of a gamma orbit with C bar, for every such Z, such a gamma Z exists. That's the first thing. Now, there may be, of course, many such elements. So what we do is we fix one, and we're going to keep it fixed for the rest of the argument. Now, well, W is in P bar, right? So, uh, um, right, and Z is in P bar. Uh, so, W is a point in gamma Z of P bar, right? Um, and moreover, uh, the angles obtended by gamma Z by this hyperbolic polygon at W is theta of Z, right? And this is because you see, let's say that W is here, and that Z is here, let's say. So when I move this using gamma Z, so I see something like this, and this is gamma of P bar, because here I'm moving it with the gamma Z, and this angle is this angle, because Morris transformations are conformal, right? So the angle here subtended by gamma Z of P bar is this one, which is theta Z. Okay. Now notice the following: if you give me any element of the Fuchsian group, uh, W is in the corresponding image of P bar. Of course, if and only if kind of the corresponding thing happens with H inverse, right? I mean, this happens if and only if this happens. Uh-huh. But this happens if and only if H inverse of W is in C, right? And this is obvious, right? I mean, if this is in P bar, then of course this one is in C, because then it would be in P bar and in the orbit of W. And if it's in C, then it's of course in P bar, because C is a subset of P bar, right? So this is also obvious. Mhm. And and this is in C if and only if for some element of C, um, this element is in the stabilizer of W. Right? I mean, this would be the Z, right? Um, um, and then one applies gamma Z, right? Um, okay, and then but then this being in the stabilizer is equivalent to the inverse being stabilizer. Uh-huh. But this happens. You see, this being stabilizer is equivalent to H being in the corresponding right coset. Right? So well, this happens if and only if H is in one of the right cosets of the stabilizer of W by these elements that take the elements of C to W. Um, okay, now uh, you see what we have found here is that uh, the element H with the property that W is in the corresponding image P bar are precisely the elements of this union. That's what we have shown. Okay, and look, and the thing is, this element, a moment of thought, tells you that those are the elements here in this sigma W. Um, so it's this nude that are the nudes appearing here that are given by this cosine. So if you look here, I mean the sum of all these angles is 2 pi, and even here. So it follows that 2 pi is the sum of all these angles. But these angles, which ones, right? I mean, it's kind of uh, you sum over the elements of C, and then over the elements here in the corresponding coset. Um, okay. Now, um, this angle, um, this angle here is equal to this angle here. So, um, well, yeah, this I will leave as an exercise. Okay, I mean this uses the fact that these are just that W is a fixed point of the elements here, and that the elements here are rotation. Okay, now you see this angle is um, you see it's constant here, right? I mean, it's kind of in this sum, I adding the same thing over all the set. So I have equal to this, right? I mean, this is added this many times. Okay. Now this one is equal to theta of z, um, right? Because this is the angle where at z, yeah? Okay, and then this is the size of the stabilizer, and the result follows, right? Because now with respect to z, this is constant, and this equal to the order of it's stabilizer, so it's by definition of the order of C, the order of C. and the sum is the angle sum of C. And this finishes the proof of the theorem. Let us see a basic example in order to see how to think about the angle sum and the order of a gamma cycle in concrete terms. What these notions mean in concrete terms. So here you can see a fundamental polygon P, a locally finite fundamental polygon P for some Fuchsian group gamma. So let's start taking a point in P. We have seen that if we take a point in P, then for any non-identity element of gamma, of the group gamma, of the Fuchsian group gamma, this element takes my point outside the topological closure of P in H. Right? So this means the image of this point on the any non-identity element is completely outside P bar, which means that that when I take the gamma cycle that contains it, that is the intersection of its orbit with P bar. This intersection has only one element, namely that point of P. So and see, for a point in P, the angle subtended by P is 2 pi because it's entirely contained in P, which is open, right? So the angle subtended is 2 pi. So the angle sum at that gamma cycle is 2 pi. On the other hand, this point also it's not an elliptic fixed point. This we already showed, and it also follows from the fact that for a point in P, every non-identity element takes it completely outside P bar. Right? So its stabilizer is trivial, and so there you can see this equality, right? This number is equal to 1, and this number is equal to 2 pi. Okay, so this is the analysis for the elements of P. The elements of P, not of P bar, right? P bar is the topological closure in H, but P itself is open, and it's not equal to P bar, right? I mean, P does not contain these shortest curves, right? Kind of the sides, these sort of sides are not really contained in P, only in P bar, right? I mean, the boundary is only contained in P bar. Okay, now next point of the analysis. Consider, for instance, let's say this point here that you are seeing here, kind of this point over here, which is in the boundary of my convex polygon, and then you see, I mean, when I click this here, the way I produce this other region is by applying some Mobius transformation in the Fuchsian group gamma. So that Mobius transformation, it definitely has the property that that P intersection its image under that element of gamma is not empty. It's actually this shortest curve, right? Okay, so for this point here, you see there are this sigma W has two elements, right? Namely the identity, right? P intersects the identity. P bar intersects the identity of P bar contains the point, but also P bar intersection this, which is gamma of P bar. Okay, so it has two elements. Now, the angles obtained by P is pi, right? So, the angle here is pi, and you see the it's pre-image under this transformation gamma. You see this other point here, this point here, and the angles obtained here is also pi, which is, by the way, the angles obtained by gamma of p here, right? Which this fact I used at some point throughout the proof, right? And you see here, so the angle sum is 2 pi. Okay, and now on the other hand, this one is not fixed by any element uh, different from the identity, right? Because um, there's no more room, right? I mean, here I already have like the identity and gamma, and there is no more room for a third element. We have non-empty intersection here, right? So this is not fixed by any non-identity element. So coming back here, the order is one, and here this sum is pi plus pi, right? So 2 pi. Okay. Um, right, and then let's say an element here. Let's say this sort of vertex, um, which is indeed a gamma vertex, right? Uh, because it's this triple intersection, right? Well, let me perform a fix. Yeah. Let's say this intersect this is just this point. Okay. Now here, um, well, my polygon was constructed in such a way that when I consider the gamma cycle of this point, that is the intersection of its orbit with p bar, that intersection contains only the point. This doesn't always happen. This is very specific to this fundamental polygon, to kind of to this very specific example. Um, okay, so there's only one element in the um, in the cycle, right? Now, um, the angles obtained by P at this point is 2 pi over 4, or pi half, which kind of you can sort of see here, like if I zoom in, I mean, this really looks like a 90-degree angle, right? Um, this on the one hand. On the other hand, when I compute the stabilizer in gamma of this point, that stabilizer turns out to be the four-element elliptic group based at this point. So, like you see, when I apply it once, I rotate by 90 degrees, then not 90 degrees, 90 degrees, 90 degrees. Um, so the order is 4, right? And here you see 4 times 2 pi over 4 is 2 pi. Okay, so that's more or less the basic behavior, and so let's go on to some definitions. An accidental gamma cycle is a gamma cycle. Here I should say gamma cycle, whose elements have a trivial stabilizer. So recall that the order of the cycle is the order of the order of the stabilizer of any of its points. Uh, So an accidental gamma cycle is a gamma cycle whose points have trivial stabilizers. Um, Notice that this doesn't prevent C from having many points. Right? I mean, as we just saw, that some points can, some accidental gamma cycles may have two elements, for instance. That's what we just saw. Um, okay, and an accidental gamma vertex is a gamma vertex whose gamma cycle uh, whose gamma cycle is accidental. Right? So every point in P bar determines a unique gamma cycle, namely the intersection of its gamma orbit with P bar. So if that gamma cycle is accidental, then we call it an accidental gamma vertex, or if you will, it's a gamma vertex with trivial stabilizer. Um, okay. Um, so suppose C is an accidental gamma cycle, so that this number is 1, mm-hmm. And this means that the angle sum is 2 pi, mm-hmm. And then we can perform a kind of a very basic analysis. If there's only one summand, right, and if C has only one point, then the angle subtended by P around that point has to be 2 pi. But this can happen only if that point, there's a disk, and a disk around that point contained in P. Um, so this means that the point is in P. So somehow the points in P are precisely those accidental gamma cycles with exactly one point. Okay, now if it has 2 points, then let's say Z1, Z2, then on the one hand, by convexity, one can see that the angle subtended at each of them by P has to be at most pi by convexity, and because of this angle sum condition, both of them have to be equal to pi. Mm-hmm. But you see, like, consider Z1. So the angle subtended by P is then pi. But then this means that it has to lie on a gamma side, right? I mean, on a shortest curve here. So Z1 has to lie in the relative interior of a gamma side, and Z2 as well. Maybe different gamma sides, but they have to lie on relative interiors, right? And this automatically implies that if my accidental gamma cycle has a gamma vertex, then it must have at least 3 elements, right? Because otherwise I would have this contained in P, but then this W wouldn't be a gamma vertex, or in the relative interior, and again it wouldn't be a gamma vertex. Okay. Now let's analyze what happens when it's not an accidental gamma cycle, so it's a bit more interesting. As we saw, being non-accidental doesn't prevent C from having only one element. Right? So again, recall that being non-accidental means that its elements have non-trivial stabilizers, but it may be that it has only one element. Right? As in the example, that it had only one element, which stabilizer had four points, four elements of gamma. Okay, so let's say that it's non-accidental with only one element. So this times this angle is the angle sum, and this angle sum times the order of the stabilizer is 2 pi. Right? So this angle is 2 pi divided by the order of the stabilizer. Okay, and this corresponds to in the example to the point where we had 2 pi over 4, and this had 4 elements. Okay. Okay. and Z is fixed by this elliptic subgroup of gamma, which is a maximal elliptic subgroup. Right? Maximal in the sense that uh, um, it is not contained in any other, it is not contained properly in any elliptic subgroup of gamma. And moreover, uh, Z is a gamma vertex if and only if this stabilizer has at least 2 points, and this at least 3 points. Sorry, and this should be obvious. And notice here that I mean, when the stabilizer has 2 points, there is something kind of special happening because then here I have P, and you see the stabilizer has the identity and the rotation. I mean, the elliptic rotation of 180 degrees, and so those are the two elements of gamma. And so this actually, so my point Z then uh, 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 is on a gamma on in the relative interior of a gamma side, and it's not a gamma vertex. Right? And in this case, when this is greater than 2, well, I clearly have the intersection of this with this. Yeah? This. Um, okay. Uh, Now, if my non-accidental gamma cycle has more than one element, then let's say with t elements Z1 to Zt, uh-huh, um, oh, sorry, more than one element. Um, well, of course, each angle is strictly less than the angle sum, and this angle sum, since each of these orders is at least two, um, I have this inequality, and so this implies, you see, this implies that it's that J is a gamma vertex, right? So, and here it is. Here you see, if it has at least one element, each of its elements is a gamma vertex, regardless of whether the order is two or not, because of this inequality. Um, okay, so uh, we arrive at the following. Um, well, if you consider all gamma vertices of of uh, of P, well, some of them may be accidental gamma vertices, so some of them may have a trivial stabilizer, or um, um, and some others not, right? And some others may be gamma vertices that are that have non-trivial stabilizers. Okay. Conversely, if you give me a non-accidental gamma cycle, you can almost always assert or assure that its elements are gamma vertices, except in a very specific situation, which is when this has exactly one element, um, and whose stabilizer has exactly 2 points. In order kind of to not have this kind of special situation, we are going to modify our notion of gamma vertex to also include such points. Right? So from now on, for us, a gamma vertex is uh, is either a gamma vertex in the old sense, or a point in P bar whose stabilizer has order 2. So, and this is, from now on, we are going to work with this new definition of gamma vertex. Um, okay, and so let's give an example of this situation. So let's say here I'm going to add this, right? And then here you can see this is a gamma vertex, gamma vertex, gamma vertex, because um, because I have a non-accident because each of them is a non-accidental gamma cycle like here for each of these 3 points. But here you see, here I have an element of order 2 of gamma, which is a rotation around this point. Uh, that point is in the relative interior of the shortest curve. So, so it was not a gamma vertex before, but now I'm calling it a gamma vertex. Um, okay.